In this lesson, we will learn about boosting. We will start with discussing how boosting works, then talk about the adaptive boosting technique, AdaBoost. Boosting is a sequential process. We start with the first classifier, and each subsequent classifier focuses on correcting the mistakes made by the previous one. In boosting, we train a sequence of k classifiers, and after learning a classifier, let's say m sub I, the next classifier gives more attention to the misclassified instances, which progressively improve the overall accuracy of the model. The process continues until we build the final classifier, which achieves the highest accuracy. And one note that the boosting algorithm can also be extended to numeric predictions, so it's not just for classification. AdaBoost stands for adaptive boosting, and it works by combining multiple weak learners to create a strong classifier. A weak learner is a classifier that is very simple and unsophisticated. So the performance is not great, but it's still better than random classification. So in AdaBoost, we create a very simple decision tree called Stump, which consists of just one split based on one feature. And because the tree has one decision node, the decision boundary is going to be a straight line. And as you can see, some instances were classified correctly, and some instances were misclassified. In the next iteration, the algorithm focuses on the misclassified instances by increasing their weights. So you can see those misclassified blue circles became larger, which makes the next classifier pay more attention to these examples. It's important to note that each iteration can select a different feature. So the algorithms can pick a feature that best separates the weights in the training data at this stage. In the following sequential step, the algorithm will amplify the mistakes from the previous iteration and hand the training data to the next classifier, where the process is going to be repeated multiple times. And at the end, the final classifier is a weighted combination of all the weak classifiers, which is going to result in a strong, highly accurate model. In this visualization, we show the impact of misclassifications in AdaBoost. In a typical classification problem, we have the xi's and the yi's, but in AdaBoost, we also introduce a weight for each example. And as we just discussed, the goal is to train the predictor on this weighted dataset where we penalize the mistakes made by the previous classifier. As you can see in this simple visualization, the first stump made 2 mistakes in the first run. Then the second stump got them correct, because you can see here the errors got amplified, but got the fourth example incorrect. So the fourth example got amplified in the next run, and so on. If you want to take a moment and think about how the loss function look like, so it's going to be a function that has a multiplicative effect on these misclassified examples. Again, in this visualization, we combine everything we said so far with the text. AdaBoost starts with the initial weights, and the weights get updated across the runs. And at the end, the classification is a result of aggregating all of those weights. Here we start to work with the algorithm steps. In the problem setup, we have a training dataset with the xi's and yi's, and we assign weights to each instance. Initially, we can assign equal weights, but as we progress, we're going to adjust these weights. Instances that get misclassified by the model will have higher weights. Notice that the weighted sum of mistake formula contains an indicator function I. The goal is to fit a classifier mi on these weighted errors. But before doing that, let's take a moment and clear up what is an indicator function, especially if you haven't seen one before. The indicator function is used to express whether a classifier prediction is correct or incorrect. In other words, the purpose of this function is to help us sum up these errors. For correct classification, we don't add any value, but for incorrect classification, we assign a value of 1. To summarize, the indicator function is important for calculating a weighted sum of mistakes made by a classifier mi, which is going to help us compute the error rate so far. We also need a stopping criterion. If the error rate is greater than or equal 0.5, then the model is essentially guessing randomly. So we better stop because it's not better than flipping a coin. The next step is to compute a quantity alpha sub I, which allows us to amplify this error. This formula seems too abstract. It's always good to plug in a few numbers and visualize it so we can understand what it actually does. So here I plotted the formula for error rates from 0 to 1. As you can see, when epsilon, the error rate, equals 0.5, the term is equal to 0. But as epsilon increases beyond 0.5, the error rate becomes worse and worse, which is a bad thing. So to summarize, we want this epsilon value to be as small as possible to ensure this alpha term is large, which is going to help us to amplify the small errors and improve the model. Next, we need a mechanism to update the weights. We use what is called multiplicative weights. The goal is to amplify the errors, and to do that, we multiply the weights by the exponent of alpha sub I and the indicator function. And here we show you how this term looks like. As you can see in this graph, we picked a weight of 0.25, multiply it by e to the power x, which is alpha multiplied by the indicator function. When the example is correctly classified, the indicator function is going to give us 0, so there will be no change to the weight. But when there is a mistake, the indicator is going to give us 1, so the weight is going to be multiplied by a factor of e to the power alpha. Now we can put all the pieces together, so this multiplicative term serves as the loss function because it's going to ensure that points with errors are given higher weights, which is going to affect the stop criterion. And at the end, the prediction is made through a weighted majority of all the weak classifiers, where each classifier's vote is scaled by its strength, alpha sub I. Finally, this figure shows the performance of AdaBoost using decision stumps as weak learners. The x-axis represents the boosting iterations, and the y-axis represents the test error. As you can see, this orange curve shows that the test error decreases as the number of boosting iterations increases because it combines more and more weak classifiers. We have two horizontal lines. The first one represents the test error for a single stump, and then for 244 stumps. In summary, we discussed how boosting works and talked about the adaptive boosting technique, AdaBoost.